Okay, so the rate of change, and then as you can see, it's right here. I tried to plot the tx as separate, so that it gives you an idea of how we handle parametric curves in dimensions higher than 2. Well, we would just do this, well, or something. We would just remove, and we can speak of space being arbitrary, and there is no reference to where coordinates necessarily. So as you can see, everything works out just fine in the computation. So you have a bunch of points. Well, what happens next? You look at well, what happened here is we concentrate on one point at a time. So that is a location P naught at where the curve itself is at the parameter equal to T naught. So that's the red dotted line. So my function f takes T naught to P naught, and so once again, think of this as the space of inputs, and you can think of this as space of outputs, which I don't want to use to stick to one particular dimension here. So dimension 2 or even 1, it could be 2, 3, or higher. Okay, so once again, the red one takes, that is a fixed location and fixed value of the parameter, and then we do we vary the other point of T naught, and we measure, it's still on the t-axis, so we measure the step by h, same name you frequently use. I think that has been happening a few times.
Yeah.
And then it shuts down. Okay. As I was saying, h is the typical name for that increment of the input parameter. So, or sometimes it's you may have used as delta x when x was the independent variable. Now it's delta t because t is the independent variable. And then you could have you can have delta x, delta y. If you have two variables, you have three variables, so delta x, delta y, delta. So you don't really want to do that. So for every dimension again. So what you do instead, you just speak of points or vectors. Okay, so either one is good enough. And because ultimately we do form, we end up with a vector. Either way, either you start with points, you take then these 2 points determine a vector, or you start with 2 vectors, and then they certainly determine a vector as well. It is the difference. So let me make that clear that in fact P naught P is the difference of the vector P minus OP minus OP naught. Okay. So if you want to do it entirely with vectors, but it's the same thing. Okay. I just don't want to draw a vector because for one, the xy axis might be different, and choosing the origin is really not necessary for this construction. But we do need for the next step. Up to this step, all we do is algebra. So algebra, vector algebra, subtraction of vectors, and scalar multiplication. Even though that scalar might be, unless it is dimensionless, it will take us to a different space altogether. But let's say it is dimensionless, then we are still in the same space. And that vector definitely, that's the vector of displacement. It is definitely in or the change of location. It's still definitely in our space. But if we go on to the derivative, then it is not. Okay, so and then naturally we proceed in a fashion that is very similar to calculus 1. We just take the limit of this. Okay, so the derivative is P prime of T naught is the limit. H goes to 0. P naught P. Let me write it out. So it will be P of I'm sorry. The name of the function was f. So it's f of t naught plus h minus f of t naught over h. Okay, so this time, once again, this is a vector. Denominator is a scalar. Okay, so altogether it's a vector. But it is once again, if units are involved, then instead of having feet measured or vector measured in feet, then you have feet per second. These are the units. Okay, so then all the machinery of limits that we spent some time developing now applies. Machinery of limits as for points in multidimensional spaces, as well as for the for vectors in multidimensional spaces. And so, well, there you go. Let me, however, do one more illustration of how this works out. Then this plan, how it works out. Okay, so let's see. So if we have a parametric curve, let's say, this doesn't work. Okay, so come back. Okay, so if we have a curve, okay, and so that's just a curve. We don't really study curves. We don't really know what curve is really. Other than it might be a curve is a path of a parametric curve, and a curve then might have different parameterizations. Okay, so and then I sample it. Okay, so I sample it, meaning that
I reported in this building. Please cease operations.
So sampled. Sampled meaning that there's a particular values of t possibly attached to each of these, say to each of these points. As you can see, they're getting closer and closer, so which indicates we're slowing down along that curve. So curve then it becomes with this not with this sampling, but with the t attached, it becomes a parametric curve. So we are studying parametric curves. But in particular, you just sample if you want to just to get started with the limit that we're going to be computing. Well, in fact, we're going to be computing limits at every single point. Okay, so then what's next is to look at the displacement. So suppose once again this is all about driving. Let me try. Okay, so then the path itself is gone. Like this. Okay, what happened? Okay. The path itself is gone, and we're left with only these points. Okay, so I tried to delete the path itself, so we're left with only the points. Let me do that again, so thicker points here. So these are the points in space of dimension of our choice. And then what I do next, I add displacements. And those are vectors, falling this way. Okay, and then, okay, I do it again. So what is that we... Okay, well, actually... Okay, that's actually what I was going to do, exactly that. So as you can see, we drew the displacements between those locations, and then we ended up with displacements living separate lives between them. So at this point, however, we need to form this term, which is in calculus 1, which in calculus 1 was called earlier here already, was called the difference quotient. This one, the limit of which we take. This one is also the difference quotient as well. And then so we divide by h, but first let's recognize that we're talking about vectors. We're talking about vectors, so in order to do anything with them, we actually have to bring them to the same spot, to the same origin. So I need to bring them to the same origin, but I don't think I can. So let's pull that off. Unfortunately, this thing just doesn't do the right thing. Let's try again. No, I gotta separate them somehow. Yeah, it's not that it's impossible. Okay, so so the point being that now I choose the origin, and then I'm supposed to copy these 7 vectors, but this time the origin will be at the beginning. So they will be originating from the same point. So let me try that. Roughly this, like the first one like this, then it turns a little bit, and yet at the same time getting shorter, slightly shorter, and then shorter, and then it turns a little bit this way, and then a little bit that way, and maybe like this. Okay, so these are the displacements, but now carried on to the same initial point. And finally, the next step is to have so these are O. So these are vectors. Vectors are f of t. Okay, so these are the vectors f of t, and then if I want to have now f of t plus h, f of t or rather over h, then all I have to do, what do I do with these in order to get these fractions? What happens to this bunch of vectors? Well, if I divide by h the same number, I divide each vector by the same number, what happens to them?
Oh, they're all scaled by the same.
They will be rescaled, so the whole picture will be rescaled by the same factor. Just I don't believe this software is capable of doing it. So, but generally, okay. So let's see. I don't think it's. I'm trying to rescale it. Just to make that point, but I guess you can. Yeah. So there seems to be no possibility. But so imagine that this one is smaller by what factor? Whatever h is. Then as h goes to 0, you realize what happens. Then starting from the very beginning, there will be more sample points, so they will be narrow, closer to each other, but still there will be denser to the end than in the beginning. There will be more points on the right. The displacement will be shorter and shorter and shorter. Okay. Then this picture will be very small as h progresses towards 0. Well, once again, these are shorter, so this picture will be smaller and smaller and smaller. What happens to this picture? Divided by h. Maybe.
Bigger,
Could be bigger, right? We divide it by h. H is getting smaller, so we are resizing, but at the same time the picture is getting smaller and smaller and smaller. So this one is just, well, I put it small here, could be larger just as well. Because all we do is rescaling, and whatever h is at this particular time, we don't know. So when you divide by h, when h goes to 0, this one, these things are going towards 0 more and more, and then you have the only chance of. That's why dividing by h is what actually creates the possibility that there is actually a limit. This is what I meant here. Plus h minus f of t. Okay, so that difference quotient, the displacement in the numerator, h in the denominator, and then there might be a limit. The limit might exist, and the issue is the same as in calculus 1. It is differentiability, and also it can be defined. It is defined exactly the same way as in calculus 1. Does the limit exist? Then you have a differentiable function. So if the limit exists, this is a differentiable function at t naught function, parametric curve. All of the facts we just talked about continuity. The relation between continuity and differentiability is the same, which is what? What's the relation between differentiable and continuous functions?
Differentiable functions are continuous.
Differentiable are continuous, but not vice versa. Yeah, so it still applies. Still applies. So if the function is differentiable at a point, it will be continuous at a point naturally. So if there are discontinuous functions, there's a gap. There is no potential meaning of any kind of derivative there because of these lines. Well, you can actually look at this picture again. And imagine that the curve on the left actually has a gap. What's going to happen is some of the displacements, there will be around that gap, the displacement will not shrink. Right? So imagine my graph looking like this, and I'm looking at once again at the displacement. One of the displacements will look like this. And no matter how small you make h, that displacement vector will remain long. It will not go to 0 as we have seen with these. Okay? So that's the problem of discontinuous functions. If it does not go to 0, but h is, what happens to this limit? This goes to 0, this one does not.
Reaches infinity.
It probably goes to infinity. Well, most likely it will go to infinity in this particular picture. Okay, so that's how the continuity you gotta have continuity for differentiability. But the main thing, as far as computations are concerned, the good thing is that we apply the fact that all limits are evaluated, can be evaluated component-wise. So all limits are, or can be, component-wise. So derivatives are evaluated component-wise. Which means that if you have a three-dimensional situation, then you have 3 times as many differentiations to do, but other than that, there is no challenge whatsoever. So as an example, let's take the standard parameterization of the circle. So it is f of t is cosine t sine t. Okay, then we already know that the derivative f prime of t is, let me give this example of how we get from point A to point B. So we go with the limit, once again, f of t plus h minus f of t over h. Okay, so I just go ahead and start writing. So I have a vector limit, h goes to 0 here, and I have a cosine t plus h, sine t plus h, okay, minus cosine t sine t over h. Okay, now I carry out all the algebra that I have to. So component-wise is a vector, so component-wise subtract. I have limit, h goes to 0. I have cosine t plus h minus cosine t, sine t plus h minus sine t for the second coordinate component. Okay, now I carry out the second, so I carried out the summation, vector addition rather, for the component-wise. Now I carry out scalar multiplication component-wise. So in other words, what happens to h? It is think of h as a multiple. The fact that it is a division, it doesn't really make any difference. It's like multiplying by 1 over h. So that is a constant multiple of our vector. So the vector in those braces, in those brackets, is our vector, and we simply multiply by 1 over h, and we do it component-wise, so each component gets multiplied by 1 over h. Okay, so I simply have cosine t plus h minus cosine t over h, and then the same for the sine. Okay, so that is your vector algebra carried out. And now we're facing the limit of a vector function, parametric curve, parametric function, let's say, that is to be the limit to be evaluated. And now by the that theorem from last week, we can evaluate this limit component-wise. So in other words, theorem. Here we're using our theorem from last week, and I have two limits. Cosine t plus h minus cosine t over h. H goes to 0, and the other one. So at this time, we just recognize these limits as what? Cosine t plus h minus cosine t over h. H goes to 0. What are these? On calculus 1. These are the derivatives. These are the derivatives of cosine and sine. Okay, so, well, there you go. And so, they are the derivatives. We know that cosine and sine are differentiable, so both of the limits exist. So these are the derivatives. It is crucial that they exist. The derivatives of these two functions. So I just write what they are. Since they are differentiable, I just write cosine t prime sine t prime, and then I just and then I know the answer for calculus 1. It will be so negative sine cosine. Okay, so we don't have to do this ever again, I suppose. If you look at the very beginning, right here, the very beginning, cosine t sine t, and then we arrived differentiation. Pretty much this is what the crucial place that we work to compute the derivative. That's what we mean by differentiation by component-wise. Each component, cosine and sine, is differentiated. That's all there is. So if it is three-dimensional, we have 3 dimensions to worry about, but 3 times to differentiate, but that's all. Okay, so let me illustrate with a little picture. So if we have our circle, so it is parameterized the usual way. So this is t equals 0, t equals pi over 2, t equals pi, and t equals pi, 3 pi over 2. Okay, so certainly I can just look at my picture. So let me repeat what I just had. So f of t is cosine t sine t, and f prime of t is negative sine t cosine t. Okay, so I can easily now confirm that my computation will match the picture. So I plug in t equal 0. Okay, if t equals 0, then f prime of 0 is negative sine of 0 cosine of 0, which is 0, 1. Okay. It is indeed the first coordinate is 0, the second one, it's sticking up. Once again, not to scale necessarily because all we can tell is that just the relative direction, the exact direction of the derivative, but not necessarily as it measures relative to the measurement of the xy plane. Okay, then f prime of pi over 2 is negative sine pi over 2 cosine pi over 2, which is negative 1 and 0. So negative 1 and 0. Okay, so you can ask, probably let me zoom in and let me zoom in on the first point, and this is if I zoom in on the 0, then you can repeat the process that we started with and do it point-wise, one point at a time. Certainly in Calculus 1, you first do it point by point, and then you do the whole thing, but we're skipping straight to function as the derivative as a function rather than just one vector. It is one vector at every point, but altogether it is not. It is a vector-bounded function. In other words, look at it. If you look at the f prime formula, it's another parametric curve. If you think about it, this is not only the original one, but the second one is also a parametric curve, which is convenient, and it is very similar to Calculus 1, where the nature of the derivative is the same as the original function. Okay, so that is not going to be the case with any kind of other functions of multidimensional calculus. But this one is, okay, so what we saw just on the picture, we would sample it. So if this is f of t naught or 0, this is say f of h. Okay, so then, and we have my, you can think of this either as the change of location, also known as the displacement. And then you imagine how this point, as h is going towards 0, what is happening to f of h? It is going towards this. F of h is going towards f of 0 because
h is going to 0.
Yes, and because the function is continuous. Okay, so once again, if there was a gap here, that would not be. So h is going towards 0 because the function is continuous. It also makes the value of the function also converge to the value of the function at that location. The displacement getting shorter and shorter. It is also, if you look at it carefully, it will be rotating clockwise. And you can imagine that it might end up vertical. It does end up a vertical vector, as you can see. This one is a vertical vector 0, 0, 1. Okay, so that is the limit visible on this picture. Okay, so you can notice also what these two vectors have in common. The magnitude is 1. It is in fact 1, and we can easily prove it. Incidentally, the word for the magnitude of the velocity is the speed. So what we're saying here is that the speed is equal to 1 for this particular parameterization of the circle. Okay, so how do we prove it? We just take the magnitude. So magnitude of f prime, which would be negative sine, we're using the magnitude formula, plus cosine t squared. And this is 1 by the Pythagorean theorem. Okay, there you go. So what it means that we have more than that picture at the top. We can, you don't want to necessarily compute the whole thing, but it is kind of important that these vectors will be all of the same exact length. As if it is you're driving along this path, circular track, and at a constant speed. So constant speed, even though the velocity is not constant, these are the velocities. You keep rotating, and you won't rotate unless you have some kind of force rotating you. Okay, so it doesn't mean that there is no force, it doesn't mean that there is no acceleration, but the speed is constant. The magnitude of the velocity is the speed. Okay, and it is equal to 1. Okay, now to confirm that acceleration actually is not constant, even though the speed is, what do we do? We differentiate one more time. So f prime of t is negative sine t cosine t. Differentiate one more time. Once again, component-wise. So I differentiate negative sine t, and I differentiate cosine t. Okay, the derivative of negative sine is negative cosine, right? And the derivative of cosine is negative sine. Okay, if this does not revealing enough, what if I factor one out, negative one out? Okay, and we recognize this formula as what? Cosine t sine t.
It's just the inversion of the circle with respect to the x-axis.
No, it's just the original parameterization or circle. Cosine t sine t is still the circle. So in other words, you can kind of say that it is f of t, even though once again the dimensions might not match necessarily. But other than that, yes. Well, I'm sorry, with a minus sign. So if we think about this, this is what we're seeing. I'm plotting the location as a vector first, so this is the origin. I'm plotting the location as my as a vector, so this is f of t. Okay, then we also know that f prime of t will be tangent, or that's the definition of tangent, so this is f prime of t. Okay, and then we know that, and by the way, you know that the radius and the tangent of a circle are perpendicular to each other. Okay, so that we know from Euclidean geometry. But now what we have also discovered is that actually if we put the acceleration in the right spot at that point where our particle is located, it will be pointing right back. Okay, so once again, not trying to do it to scale because the scale might be all messed up, but it is pointing pretty much back like this. So this is a double prime of t. Oops. Okay, and that proves something nice, not proof, but it gives evidence to a nice observation is that acceleration is force times, or the force is acceleration times the mass. Mass is just a constant, so it doesn't change the direction. So we can then conclude that the force is the points toward the origin. Okay, so if we have any kind of orbital motion, then you realize that whatever you're rotating around actually serves as something that pulls you towards it. Okay, so that's certainly what Newton did. Explaining the geocentric, heliocentric model of the solar system, which is now that, well, it makes sense to call it solar system if the solar is in the middle, because now it's not just by magic that the Earth is moving around the sun, but rather the sun is pulling towards it. If you look at this picture, you realize why it is. It makes sense. So even though it is pulling towards it, just like an object being pulled on the Earth in the same manner, except why don't we fall on the sun? So the force is pulling us towards the sun. Why are we not falling on it?
Because we're moving in our orbit, falling around it, not straight towards it.
Right, this one. The velocity is what makes a difference. So even though the pull is towards the Earth every time, but we are moving away. So in other words, what the force does, it only turns this thing, because in the next moment my velocity will turn, So the force is there, it's pulling towards it, but it's not pulling hard enough for us to actually turn around and fall on the sun. So in other words, it takes a good speed to begin with in order to avoid being pulled and drop on the sun. Okay. So, and then what certainly Newton did more than that. He did the same with ellipses, because he already knew that they were ellipses. The orbits were not circles. They were ellipses. And incidentally, another thing for us to note is that the magnitude of the acceleration is also one. Yes. Okay, so if the distance is constant, okay, then it is parametrized. Actually, more important observation to make is the relation between the speed and our parameterization. And parameterization is meaning of t is originally we think of it as time, but really why it all works out is because the angular velocity is constant. So the t is at the same time, it is time, but it's also the angle. Okay, so as t runs between 0 and 2 pi, we make a full circle and we go at straight every moment of time. We cover the same distance, same angle. Okay, so that is why the speed is constant. So every time you will have at one moment of time you have this, and then at a different moment of time you have that, but the angle is the same. And therefore, the distance covered is also the same. And that's how you get constant speed. Okay? And then the acceleration turns out to be also constant, so there's also nothing going on there. It just pulls a constant speed, as we now know, it depends on the mass of the two objects. But other than that, nothing else to worry about. So we'll do this. I don't think I actually stated what the parameterization of the ellipse is. So let me give you that. So the ellipse, the actual orbits of the planets around the sun, and let me use the notation that we have. So f of t is a cosine t, b sine t. So these two numbers a and b give you the stretch of the ellipse in the two directions. Okay, so this will be a and this will be b. Okay, so what is the difference? If let's just quickly review what the consequences these two numbers that are not equal to each other anymore. So first of all, you realize that what's going to happen if the radius is not 1? I guess I'm getting ahead of myself. Let's first quickly ask ourselves what's going to happen if the radius is not 1. So this is the circle, radius 1. What if it is not 1, which means that I'm going to have a radius r in the beginning of in front of my vector. Okay, so how would that affect our computations? Not by a lot. I was skipping this part already, but I'm going to have simply another r in the middle, in front of it. Okay, so and then I will have r in front of this. So I mean, this is what we call the constant multiple of differentiation. It certainly applies to vectors as well as to functions. And if we move on here. So everything gets multiplied by an extra number, so everything will be stretching more. Say r is 2, then everything is doubled. The velocity will be doubled as well. The acceleration will be doubled. So then the speed will not be equal to 1, it will be equal to 2. The magnitude of the acceleration will be also 2. Okay, so but otherwise, other than that, there is no change whatsoever. This picture will be exactly the same. It is just an illustration. So a radial force doesn't matter what the radius is. Now, but if we have an ellipse, then that certainly changes things, because where it's going to change for the most part is differentiation will still go through, right? So it will I will have like a here and b there, a here and b there. So that still goes through. The difficulty of there is no difficulty of computations, but the Pythagorean theorem won't apply anymore because we're going to have A here and B here, and so it will add up to a number that is not 1 anymore, or anything. It will not add up to anything. So you won't be able to cancel t. So this is the main thing why this the answer is so nice is that t disappears and the speed is constant. When I have A here and B there, there won't be no cancellation. The Pythagorean theorem doesn't apply, and so in other words, the velocity, the magnitude of the velocity, the speed will be variable, and so will the force. How come? How come? Anybody knows why? I mean, you do expect that the force to be, for the ellipse, is to be, it's the same situation. You have the Earth, you have the Sun, they're pulling towards each other, so the force is constant, and it doesn't appear to be constant. Well, let me confirm that. Let me confirm that this the by differentiation. So f prime is negative a sine t, b cosine t. Second derivative is negative a cosine t, negative b sine t. And either one, the magnitude you take is not constant. Neither force nor velocity is. So these are, all of them are variable. Well, what I meant to say is not that. What I meant to say is that the magnitude of either one of these vectors will be 1. Variable when A is not equal to B. So why is it not working out with the physics of the situation?
Because the distance to the center is changing.
Yes, it is changing, but actually, that's not it really. I mean, the distance is changing. Just because it's changing or not changing, we actually could move around the circle in such a way that there is acceleration. If we're just moving at a constant speed by setup, but you can actually follow the same path, going faster and faster and faster and faster. So the relation between the distance really is not it. The physics, I intentionally messed up the physics here. Where is the sun?
Is that the intersection of the two axes?
No. It's in the focus. It's in the focus of the ellipse. Okay, so I don't want to just define it again, but not only that is the problem. So then would still, the distance would be still variable, and it would work out. But even a bigger problem is that this is not the right parameterization. This is a parameterization in the same way as the circle. So the parameterization works like this, that what we have is this. Equal angle at equal time. But that's not how we travel around the sun. This is roughly, well, maybe somebody remembers how it works. We are moving slower here. And then we speed up. Okay? So it's more complicated motion. And the Kepler's law of orbital motion is that the area is constant. Hold on a second. Did I do it right? The area swept by the radius, not real radius, but that segment between the Earth and the Sun covers or spans the same area at every period of time. Okay, so which means that so this one has to be thinner. It is. I did a job. It has to be thinner.
think it's supposed to speed up as it gets
Right,
closer.
exactly. I now see that I messed up entirely. Yeah. So as you can see the picture, what I was just doing now is that this has to be, because it is shorter, it has to be wider than the one that is longer. Okay, so it is actually goes slowly close to, when we're close to the sun, we're moving slowly. Okay, so I hope this picture is more revealing. So anyway, so the point is that it's kind of complicated. The motion isn't as simple as you think. Something like that. Well, it's not always, but close enough. Okay, so then you have to look at it in a totally separate way. And then it works out. That's how Newton discovered that actually there is a pull towards the sun that is located in the ellipse. So once again, the my speed would be tangent. They always are, but my acceleration will be pulling me towards the sun. Okay, so once again, so this is F double prime, and this is F prime. Okay, so the next topic is, so that is still to be considered. It lists one of, either in class or probably one of the projects. And the next is following the pattern of calculus 1 is rules of differentiation. Rules of differentiation, and the rules are the same, just like for every law for every law of limits, there is a law of differentiation. So just as we don't have division for vectors, we don't have a quotient rule for vectors either. So, but otherwise, we have the sum rule. So say f plus g prime is equal to f prime plus g prime, as you can see. So you can apply the rules right there without breaking them into coordinates necessarily. So that certainly takes time, and there is nothing there hiding from us any particular information. We can just take the whole thing, use the vector notation, and derivative is the sum of the derivative is equal to the derivative of the sum is equal to the sum of the derivative. Same for differences. Okay, and then we have a constant multiple rule. So Cf prime is equal to C prime. And then we have the two product rules. The two product rules. So if C of t is a variable scalar function, then we do have to have the two terms. Okay, we'll just do it next time. Okay, so. Or if you like to call it the variable multiple rule. Constant multiple rule, this is variable multiple rule.